Hey everyone, welcome back to Unproven Tech. Thank you so much for showing lots of love, and we got tremendous reaction and views on our recent, having the last system design mock interview video, where we discussed designing lead code. And in this video, we'll be following the same pattern, but this time I'll be the interviewee and Vanshika will be the interviewer. Let's proceed. Hi Vanshika.
Hi Anubhav, how are you?
I'm good. How are you?
I'm good. So, as you all know, today we'll be doing a mock interview for system design. And this will be particularly for people who are targeting SD2 or SD3 roles at product based companies or FAANG companies. So, I will be your interviewer for today, and you'll be behaving as the interviewee. So, let's
Sure.
get started.
Sure.
Okay.
Meanwhile, I'll share my screen.
So, we want to design a system which will retrieve the top K or top N videos on YouTube or maybe even YouTube Music. Basically, something like a top K heavy hitter.
So essentially, we want to design top K heavy hitters or products like YouTube videos, like trending videos, top 10, top 20, top 110 trending videos,
Yes.
and trending music or YouTube music at the same time. I mean, this can be also extended to getting top K Google search, top K most liked or most purchased product on Amazon, Flipkart. Is my understanding clear?
Yes, it is. You can use it for Spotify, even
Yeah, I mean, yeah,
some other tools
the
like
same thing, right?
Confluence or Google also. That works.
Sure. Okay. So I'll start with some functional requirement. Okay, the very first functional requirement that comes into my mind is to get top K from like for follow YouTube videos or YouTube music, like or any other system, to get the top K trending elements, and which essentially takes K and the time window maybe. Yeah. And the second that comes into my mind is to record those events, because essentially in practical life we see these events, which will be a user clicking a video or a user playing a music. It's an event, and we want to record. Our system should be able to record those event to process further to calculate the top K.
Sounds good.
Okay. Now, coming back to the non-functional requirement.
Before we proceed to that, for the functional requirement, do you have any questions with respect to what the size of K could be or how the time window could look like?
So, thanks for bringing it up. I think I didn't make an assumption, but ideally I should have asked this in the first place. K, what numbers do you have for K? I mean, it's a product requirement, but talking more practically, a user stops scrolling after 100 trending videos or 100 music. But even to scale it further, I would say K less than 1,000 would be a good number, because a growing K would be negatively impacting our decisions that we take forward.
That sounds good. So the cap for K is indeed 1,000. It should be, at least for this interview, we should scope it down to 1,000. And with respect to the time video, the time
Yes.
window, do you have anything in mind?
Yeah. So I would like to take it this way. The time window could be any arbitrary window, or let's again consider the practical product requirement, where it could be last 1 hour, last 6 hours, last 24 hours, last 1 day, last 7 days, last 30 days. These are some of the time windows that we usually see on these products, even on Spotify, YouTube Music, or YouTube. So it could be last, let's say, 60 minutes. Even we can talk about how we can last 1 minute. But practically talking about last 1 minute, then that depends on the product again, that we want our user to be able to notice the refreshes that happening in the UI. I mean, do we want to refresh the UI of top trending, top K elements on YouTube or Spotify or any other website like every 1 minute? Because that is something that we might need to discuss. That do we want our system to support last 1 minute, last 5 minute sort of requirement, or like. Mhm.
So to begin with, I don't think we should consider 1 minute and 5 minutes. We can take it up later on if we have time. But for what I have in mind for today's interview, I think last 1 hour, 7 days, last 1 hour, 1 day, and 1 month should suffice to start with. And later on, you can take up the other aspects in case you have time.
Sure. Also, would like to put more freight on the record events. Essentially, in record events, we would like to capture event ID along with the user ID. I mean, we keep it as a metadata because we essentially don't want to. I mean, we really don't care who was the user which watched most of the videos, but we rather care about which event ID appeared. I mean, the frequency, the count of that event ID that will make it okay. And also the rather I'll keep event time as an important attribute for aggregation. I mean, this is very important because we want to aggregate for, let's say, last 1 minute, last 5 minutes, 60 minutes, last 1 day. So event time is the time at which that particular video and song was played. I mean, the time of that event happened. And then some other metadata like user ID. Also, another aggregation metrics that we can talk about later could be location where this video was played. I mean, it could be US, India, because we also have product requirements like get top K videos for India, top K videos for US, top K video for Israel, China. I mean, any location wise. I mean, it could be country. So essentially, we also want to take consideration, but we can talk about this later.
Yeah, I agree on
Country.
that. In fact, in my opinion, for record events in general, I would first like you to dig deep into get top K, and then maybe we can discuss about record events.
Sure.
Yeah, so we can discuss
So
the functional requirements fairly quickly, please.
sure. So considering the scale that YouTube operates, or even Spotify and other similar platform where we'll be using this top K feature, let's only talk about YouTube. YouTube has around 1 billion, I think more than a billion unique videos. And considering this number of videos, and essentially we are seeing new addition. I mean, it's growing at a very fast pace because after OTT and a lot more things are happening. So this is a growing number. And at the same time, I can safely say this number can lead to somewhere around 100k QPS. We can easily see, which is like 100k QPS of events happening. So events, which is like live streaming of videos, or it could be users watching videos, or like hundreds of thousands of users might be concurrently clicking different videos altogether. And also this is an increasing number. But for the sake of interview, is does the number look good to you?
Yes, for unique videos, for the sake of the interview, I think let's not go up to 1 billion. We can restrict ourselves to around 1 million also to begin with. And then we can discuss some more strategies later on if we have time.
Sure. I think for me, I think it's fine to keep 1 billion unique videos. I try to keep it as practical as possible. And also considering these two numbers, this highly sense that our system should be highly scalable. Basically, we should have high throughput because this number itself said that if the system is not able to handle this much of QPS, a system shouldn't break. It should be able to scale easily for these numbers. And then our system should be highly available as well, which means a system shouldn't die even if one of our nodes or due to any failure. It should be partition tolerant if the network goes away. Even let's say if a user event is not propagating, let's say if a user is not in a network area, even after when the network comes back, we'll be able to get those events. Or let's say even there's a network failure within our system, it should recover fast and should be highly available. And we can say we can target four nines of availability for now. And then considering the another very important non-functional requirement would be low latency of the reads. Low latency of our get top K videos. Here we want basically this is the read part of our system where the user essentially wants the top K videos. And we want, especially for smaller duration windows, like 1 minute, 5 minute, and even last 60 minutes. Because why this is practical? Because let's say any viral event happens. I mean, let's say RCB wins which already won. So there would be like tremendous amount of videos around where we want to capture this, which happened in the last 60 minutes. So we want to capture the viral moments and bring it back into the rank of top K.
Okay.
So does it sound good to you?
Yeah, I just have a small quick question. Would you want to quantify low latency in terms of
Yes.
seconds if possible?
So when I say low latency, it should be as close to the real time. When I say real time, it should be sub millisecond. Let's say less than 100 of millisecond of latency.
Sounds good.
Right. And we can definitely talk about uh, where we want to aggregate for a day, 7 day, and 30 days, which can't be low latency because the scale is huge. And we will talk about this in our design decisions. And let's just keep it parked here. So the another important when we say low latency reads of close to real time, then the picture comes clear that we have to talk about the accuracy of this thing, accuracy of get okay or smaller duration or smaller basically recent smaller duration. Essentially, when we talk about low latency reads call, so we have to talk about the accuracy of this top k essentially for the recent duration like 1 minute, 5 minutes, 60 minutes, and we have to talk about like eventual consistency, which is like our when we say eventual, it's like approximate approximation of the result that we'll get versus the strong consistency of where we want the accurate results. I mean, definitely for last Monday, last 7 days or 30 days, we want accurate results because we will be taking more time to calculate it okay rather than we'll be spending less time. We want to spend less time so that it is as close as to the real time, and which itself tells that we can't do heavy lifting, any mathematical operation which takes more than 100 milliseconds or let's say 200 milliseconds. Does it sound good to you?
Yes.
Okay. Sure. So I'll start with the basic design. So here is my user, and so basically my user will be interacting with my API gateway. So this is how we'll so this event will be capturing from the user. It could be from the mobile, desktop, or like any source of the truth that we have. And this API gateway will be responsible for having basically aggregating and sending the events further down to my service, which will be essentially calculating the top K. So I just want to quickly talk about how this thing would. I mean, how will we essentially calculate the top K, which is pretty intuitive, and it's in a classic DSA problem as well. So let's say we have a single machine. For a single machine, it's very simple. We'll maintain a hash map, and we'll also maintain a min heap of size k, which will be essentially storing the top k top k elements, and which is essentially the top k trending elements, the trending videos or songs for us, right? But having this said, maintaining a hash map, which will simply store this thing, the event ID and its count. So whenever an event happened, we have we just discussed this thing, right? The recount event. This is like sort of schema that we'll be having. And this with this event, we'll be trying to populate our hash map and also maintain its main heap of size k. But this solution won't scale because we'll be seeing 100Ks of QPS. Yes. And this is storing a hash map which essentially can grow up to a size of 1 billion of YouTuber videos, or let's say even 10 million videos. It will be a resource constraint because insertion is fine. Insertion is like log of n because it will take the memory constraint. We might seeing out of memory issues because essentially if it's a Java service, we'll be spending a lot of time getting spent in our garbage collection and all. And also for min heap of size k, we don't see any challenge because this K is, I think, less than 1,000, and it won't really take any much space. But this hash map is growing.
Yes.
I mean, it grows. I mean, the cardinality, the hash map grows with the cardinality of the unique videos.
Correct.
Grows and doesn't scale. Right? For a single machine. So when I say a single machine, which means I want something like this. I mean, from this, we will be sending this. Let's call it as a or processor machine or processor node, which essentially does this thing, which will like maintain a hash map and a mean heap of size k. But as we discussed, this one scale and also I see. Do you see it? Do you feel the keeping a small service within an API gateway? I mean, I would say this would be my uh my a small. We can run a sidecar within our API gateway, which would essentially do some transformation on this event ID we are receiving and send backs to our processor node. It's like another machine running. So it will say aggregation service, which aggregates and send back to it. But the challenge, the drawback I see here is this won't scale because essentially API gateways. I mean, it could be a design discussion where we want to discuss how much CPU and memory does our API gateway has, and running it as a sidecar will be seeing any side effect or not. So rather than having this tightly coupled, I mean, this service should be aware of what my processor node accepts accepts as a form of input, and it makes the system very tightly coupled. And also it depends. I mean, it is bounded with the API gateway memory and the CPU and also the network latency and a lot more things. I think for this reason, I would recommend, rather than this, I will be introducing another partitioner, Kafka. So now essentially, instead of doing a lot of aggregation and stuff, the whatever event we are receiving will simply drop it over Kafka topic.
Okay.
Kafka topic. It could be any name. I mean, it's fine to or something right now. So why Kafka? So Kafka essentially, I think it's a very popular partitioner and it scales very easily. When I say very scales easy, Kafka can easily handle millions of queries per second. And since it is like partition, it acts very good partitioner, and also it provides you out of box. It provides you out of box the durability thing. I mean, for a Kafka, it is simply a like distributed streaming platform. I mean, where you can just drop all your events, and the consumer nodes, which is essentially the processor node, can process those events at their own pace. Now, at least this part of thing can easily scale because
Could you clarify one thing? So, are you thinking about just a single Kafka topic for now, or do you expect to have multiple topics? And um, what is the sort of partitioning strategy any you are planning to use?
sure. So I was about to speak on that. So for this Kafka, we'll take a we'll partition on event ID. When I say and a partition on event ID, so it means all the event that all these similar event. I mean, Kafka guarantees is all a similar event will go to a single partition, and we can talk about. Let's say we start with 10 partitions, and which will essentially grow with the number of growing unique events. So, but when we partition on event ID, so that has some drawback as well. When I say a drawback, it could be it could lead to a hot partition where a single partition will be receiving a lot more events because let's say a particular event is very viral. Let's say Virat Kohli uploaded a video, and all the Virat, let's say 1, 2, 3. This is, let's say, this is the event ID. After partitioning, I mean, we do hashing. Essentially, this is what happens internally inside Kafka. We do the hashing and we get the out partition number within which this will go, right? And let's say it goes into partition 2. So all those events, which could be like millions of views, can potential views to billions of views, will be within a single partition, which will create hot partition, which is like essentially creating a skew. I mean, where one partition we're seeing a lot more events, where the other partition has less events. Does it sound clear?
Yes, similar to a hotkey problem. I think that
Hotkey problem. In exactly. To solve this, we would rather keep it very simple. I mean, we'll just say instead of hashing it directly, we'll also add some salting. I mean, we'll do salting. So what salting does is, let's say this is a hash function. With the event ID, we also add some random number. Let's say it could be between, let's say, 1, 2. I mean, any random number, and then do the hashing. I mean, whatever hash function we have. This will guarantee that now this would look something like this. I mean, now we have 1, 2, and similarly we have any events. I mean, where each ID will, let's say, have 20K views, will go into different partitions.
got it. Makes sense.
Makes sense, right? So, but that needs to be talked more about the processor node, because right now we have a single processor node. A single processor node can't handle a QPS of 100K. I mean, this Kafka topic is receiving tremendous amounts of event, which is essentially at a scale of 100K, which can grow even up to a million QPS during peak time, right? So the idea is very simple to have when we talk about Kafka, it's a very popular term, which is like consumer group. So we'll have a consumer cluster, which is essentially our processor nodes only. So we'll essentially scale it. So instead of, we'll have a...
You specify more on the processor node. Could you let me know one thing? So here you'll be using Kafka only as a streaming platform, right? Not as a queue, or would you want to use it as a queue as well, if required?
So when we talk about Kafka, so Kafka is not like it's a messaging queue, but it also provide more features like replaying your event. I mean, at any point of time, you can replay. You can just provide the timestamp ID from where you want to replay, and also you can also provide the retention period for how much long we want to retain the events for replaying, and also it provides good durability as compared to any other messaging queues like RabbitMQ. Here, Kafka is just used. It's like a PubSub thing, not even PubSub. It's like a broadcasting. I mean, the API gateway will broadcast, essentially unicast all the events that is coming to API gateway directly to Kafka topic without even knowing what is going further. So this beautifully decouples our resource event logic. I mean, the ingestion. I mean, the ingestion is not decoupled, and the API gateway, at as dumb as possible, just drop all the events to a Kafka topic, basically a Kafka a partitioner, and from there we'll spin up a consumer node, basically consumer cluster, right? So this is our consumer.
Basically, the processor node.
Yeah, basically, in Kafka world, we call it consumer nodes, which is a group of consumer nodes called
Consumer.
a group of consumer group, which essentially subscribe to this Kafka topic. And since Kafka is able to handle millions of QPs, that doesn't mean all consumer nodes can. It would require a lot of CPU and memory to do that. But now here with this architecture, the consumer node can consume events at their own pace, which totally depends on the maths of how much CPU and memory you have. I mean, the more you give, the more at a pace they can. I mean, then there again terminologies like we want to do a batch of. I mean, we poll batch of 1K events. Also within Kafka, in Kafka, only one consumer from a consumer group can actually consume from a Kafka partition. Let's say Kafka has 10 partitions. So only, let's say, and also we have consumer group of 10 nodes. So each node will talk basically consume to sync like each partition, so that we have maximum throughput. And this we can vertically scale. I mean, we can vertically scale consumer nodes, or also bringing up more consumer. Like, there's also the number of consumers and the number of partitions. Like, it's like you might ask this question, why? I mean, we can increase the number of partitions so that then we also have to increase the number of consumers to have the maximum throughput, because it is like dependent. You can have like there's no limit on having number of partition, but this partition is limited by your consumer nodes, because there we have a limitation. We can't spin up like infinite consumer nodes to have a very high throughput. So which is limited.
Can you discuss a little bit about consumers subscribing to particular topics so that?
Sure. So within Kafka, let's say we have a topic, top, let's say event, YouTube videos, click events. Let's say this is a topic, and within this topic, let's say we started with 10 partitions, 3 days of retention period, which essentially means Kafka will try to retain your data for 3 days, and after that, it will be deleted. Not even soft, it will be hard deleted. And then we also decide. I mean, this partitions is all taken care. I mean, how it will be created is internally taken care by Kafka, and then we have our consumer groups, which are like consumers. They essentially subscribe to this Kafka topic, and when they subscribe, we have to define a concept. Like, we have a consumer group ID. So let's say we spin up let's say 10 processor nodes. I mean, which is like 10 different machine, and we assign same group ID. So Kafka will be internally able to identify that these nodes, processor nodes, which like essentially machines, are subscribing with this same group ID. So these are part of a single consumer group. So then the golden rule of Kafka kicks into picture, that within a consumer group, each consumer can only subscribe to, I mean, it can talk to a single partition. Does this sound good to you? And then internally, based on whatever the speed of at what pace we'll be polling the events. I mean, when I say polling, it's like consuming event. We have also defined. Let's say we say we'll consume every second 1K events, 1K event from our Kafka. So Kafka also maintains a global offset. So let's say consumer A. Let's say this our consumer node A. Consumer A reads 1K events. So Kafka will internally update that offset, saying that these 1K events are already captured or taken care by your consumer A. So you won't need to be further. I mean, this thing comes into picture because we can have multiple consumer groups, and that only comes into picture when we want to have different business logic. Let's say consumer group A, which has, let's say, 10 nodes, is listening to the event and doing some processing, which could be some transformation, some MapReduce job that we'll be discussing further, and since do this downstream.
I think I get this. We can
Yeah.
move ahead.
Sure. So yeah, this is how internally Kafka works.
We can now focus on the other architecture. I think I understand how you plan to use Kafka here.
Yes. So now we'll have these consumers group. So what they're essentially doing it now is, all these consumer nodes, each consumer group is talking to a particular partition, and within the partition, the Kafka guarantees that all unique, all the same events will be in the same partition. And now we just also discuss the salting thing that we'll salt, and then it will be distributed. But there's some drawback as well. Now, it is like, now for this particular event, essentially what we started was that each partition, I mean, each video ID, I mean, it's like event ID of like similar video event ID will be in a single partition. But now this is breaking. I mean, now it is like distributed into different consumer nodes. So this consumer node, what essentially is doing the same thing which we discussed that a single machine would be doing, right? Like having a hash map which counts the frequency and a min heap of size k to essentially calculate the top k. And now each consumer or processor nodes have their local a local top k, right? And did you get this? I mean, the local top k, I mean local k.
Yeah. I think
this local top K is now with let's say with 10 consumer nodes. Now we want to flush out everything. We'll fan out, let's say every 5 seconds. Every 5 seconds is fine because every 5 second why every 5 second I said because the UI we might want to refresh every 5 seconds, because refreshing every 1 second would be uh, very heavy on the UI as well, and will be not a good experience to the user because they will be seeing refresh and the elements rearranging every 1 second, which is like bad experience. Like if refreshing every 5 to 10 seconds, fine. So every 5 second they so basically they do the maths, which like hash map and many thing, calculating the top K, and every 5 second they flash out to a service layer, or which will like our bread and butter for all the system, which serves the top K or its service layer, where we essentially have a host machine where we actually do. Let's talk about this. What maths is done here is we have local top K from 10 different groups, right? 10 different nodes, 10 different machines, 10 machines. Now we want to get the top K. Basically, we have to sum or merge all these top K, merge local top K to get a global top K. Does that make sense?
Yes.
Which essentially has global top K, which this host machine stores internally within the RAM or something.
Sounds good.
Sounds good, right? And then we have our another user, which is trying to query query it last, let's say 60 minutes
Okay.
top K, which will be served from this service layer back to the user.
Got it.
But I see some challenges here. Challenges here is again the hash map thing. I mean, the hash map is a growing data set. I mean, why? So let's say hash map at a point hash map would have to. I mean, I didn't discuss how would be calculating the global top K, which is again essentially having a hash map to some basically. Again, it's a very popular DSA question of merging K list, and we have the same thing here. So we'll be having a hash map and a global min heap to track the global top K. I mean, we have a hash map where we have global hash map.
Yeah, I think I.
And we'll be okay. But the problem is hash map is growing. I mean, at a time. So at a time, there would be like millions of unique events. Where this hash map size will grow up to like tens of GBs of data, which is like very impractical, and it doesn't scale with the cardinality of number of unique events that we might receive, because it's a growing number at let's say 10% or let's say even 5% every year on year. So there's a trade-off which we can bring that I talked about, is that instead of using hash map, we can use like a count min sketch, which is like a probabilistic data set similar to Bloom filter.
Yes.
We call it CMS, count min sketch. It's a probabilistic data structure which we'll be using to do the counting. I mean, we use this to count the frequency of each event happening. So do you want me to go through the internal of CMS and how we'll be using the CMS to calculate the top K?
Can you just briefly describe it to me? Because I would want to focus more on the functional and non-functional requirements that we have written. So latency is one thing that we have not discussed yet. So
Yes.
you can dive these ones if we have time post that. But right now, just tell me in short.
Sure. So CMS, it's like a 2D integer array, and where we'll be storing we'll have a width which controls basically CMS comes with a trade-off that with CMS it doesn't grow with size. I mean, let's say we decide the width of CMS to be 2000 and the depth, which is like let's say 7, which this maths which is like width and depth, like matrix and cross M. This gives that 1% approx, 1% error that we are okay to have in our talk K. I mean word percent and 1%, okay, which is like 99% accurate results and 1% error chance.
Would you like to map this to which of the requirements you're actually tackling by using CMS?
Yes, exactly. So the low latency thing. I mean, this low latency thing. Now we have a CMS, and this would take, like, if we do the maths, it will simply come to some KB. I mean, it will never grow because it is like fixed size. It is not growing. So it will hardly take your 50 KB of space in your consumer node, which is like very practical, very cheap, and it never grows with an increasing number of thing. And now when we do, let's say now if we don't do it, right? One, we'll be running out of memory, and then the calculation time, basically inserting in a hash map, which rebalances whenever the size grows, and then min heap is again, we'll be using min heap of size k to calculate the talk k. But hashmap we can completely replace with CMS, but this comes at a trade-off where we might not see 100% accurate result, but CMS also guarantees that it never underestimates. I mean, it always overestimates the results because of the internals. So let's say if it says, let's say if a video has, let's say 1 million views, it would rather report at, let's say 1.01 million, which is fine when we are doing, when dealing with practical events happening, viral events. We really don't care about a video having 10 more views than it should be actually reported. It comes with a trade-off of accuracy versus the low latency.
Sure. Do you also feel that this could also be taken into account for the accuracy pointer that you had mentioned in your non-functional requirements?
Exactly. So when we discuss I mean, we can have a system where for smaller or recent duration, where we want to provide the user real-time refresh, we can use this architecture where we have a CMS. We update it the CMS, now we have to maintain a local CMS for each consumer node, and then this service layer have its own global CMS, which will be again updating. I mean, CMS is like linearly combinable, which you can, I mean, let's say you now have 10 CMS. You can literally do a summation, like addition of doing a matrix addition of these 10 CMS. You'll get a global CMS for, let's say, global CMS, which is, let's say, for last 5 minutes, or let's say 6 minutes, or sorry, 10 minutes, or let's say 60 minutes. Again, the trade-off is that we'll be seeing 99% accurate result and 1% chance that this 99% accurate result is not correct. But only overestimates. And we might go into the detail of CMS in the end of the, we can dive deeper, but this is what I want to propose for when we want to have low latency, but we are good with approximate results. But now let's talk about let's talk about the path where we want last 1 day, last 7 days, last 30 days, and the business justifies this because business and the product might come that we want accurate results, because we want to accurately give credits to the creators or the authors of those music and videos when we try to publish last Monday, last 7 days, and last 30 days of this thing. I mean, imagine, because there's this in this data streaming pattern, when we try to design, there's a very common thing called long tail problem, where, let's say, when within this what the problem is, let's say a video was ranking, let's say we want to get top 10 for last 1 day, last 10, like 24 hours. And we are maintaining, let's say we are maintaining 1 hour CMS, basically 1 hour CMS, and we want to combine it to 24. I mean, last every 1 hour CMS we can combine and get a 24 hours CMS, like which is 1 day. But let's say a video which is ranking 11th on each hour, which might result into rank 1 in total summation. I mean, there's a complete data loss because we are only storing top 10. We don't have any information. We are discarding anything after 11th. But there's a very high probability, and it is that we might lose data and we might lose the actual information, which is like approximation. So for this reason, for the accuracy reason, the product would demand that we want to have a path where we calculate the exact count. It's like highly accurate, but we are processing a lot of data, like millions, like essentially terabytes and petabytes of data. So for this, I would say having another processor node or having another consumer group, and we don't have these kind of things here now. Or consumer group, which subscribes to this Kafka topic, or like so basically nodes, which essentially reads from this Kafka topic and does a data dump into any data lake or like S3. Does sound good? So it is, let's say, a data lake. It could be like Hadoop, SDFS, Hadoop distributed file system, or S3, or even Google Cloud Storage Service.
Could you tell me why do you prefer to use a data lake here instead of a data warehouse or a data mart? In brief.
Okay, so essentially what's happening, if as we are seeing 100K events per second, and if we, let's say, even if we can assume that one event might take, let's say, 10 bytes or something, within an hour we'll be having GBs of data, and within a day we'll be having petabytes of data. So when we want to deal, and it's a very classical problem when you want to deal this much of data, because we'll be running an aggregation, and we'll be talking about it, we'll be running an MapReduce job on the top of it. We want this data to be stored in a durable and in a cheap machine, because we also don't want to waste a lot of cost compute in just storing. So data lake is like data lake or data warehouse. It's like a very obvious choice here, very obvious choice, where we just dump, like without just knowing anything about it. We, whatever you're receiving, we just dump in SDFS or S3 or GCS. Choosing between SDFS or S3 is not a very complex decision. It's a matter of cost, because SDFS, it's like a distributed file system where it is managed by Apache Hadoop, where we create multiple partitions, and let's say 1 terabytes of data is now is not chunked into multiple small files and now stored into different machines altogether. And those machines are really cheap.
Yes. Okay.
And
so
we can run MapReduce job or Apache Spark job on the top of it. And when our question would be, why don't just use simply S3? It's a decision of a comfort or choice, or could be cost as well for some companies, because ingress cost for this S3 like this service like S3 and GC is almost nil, like very cheap. But the ingress, the outbound costs are very heavy. Let's say you want to download these files or extract these files later, and at any point of time, it will be very costly. But SDFS, any company can buy on-premises machine and just run this, because it's an open source thing.
Sounds good. One other advantage with a data lake you could have is that you could store any sort of data, either structured or unstructured, in it without worrying about having to change all the data into a particular format to store it in your sort of data.
Yeah. That is, it comes with multiple advantage. In our case, we really don't care about the data structure, because when we started our data, the schema is already flat and denormalized. So which essentially is fine. So now when we have this data lake here, from here we can have another MapReduce job. So MapReduce is like a programming paradigm which was introduced by Google back in 2024. They published a white paper where they used MapReduce for their internally, and where they actually indexed the complete internet, World Wide Web. And then MapReduce was later, MapReduce mostly, it is very much inspired with the functional programming. If you know, in Java, I have personally worked on reactive Java programming, where it's almost like monoflux, and the map and the reduce, the lambdas, we use it a lot there. It's highly inspired from it. So MapReduce, it's a very straightforward paradigm where, and also if you've heard of Apache Hadoop, Apache Spark, Flink, it's all based on MapReduce. Even the Apache Hadoop, when it was introduced, it was like the internal architecture and the core is powered by MapReduce. And the successor of it, which was like Apache Spark, and I'll also propose using Apache Spark here, which is like at this point of time, when we have Apache Spark, we really don't care about manually writing MapReduce jobs. We have Apache Spark, we can configure it. And why Apache Spark, why not Apache Hadoop? Because Hadoop essentially writes the intermediate data into disk, which is apparently slow. And whereas Apache Spark writes into RAM, which is very fast and also provides batch concurrency. And it has many benefits, which we can dive deep when we have some time. So we have this MapReduce job. which is let's say running every 1 day, 7 day, and 30 day, right? So it can run overnight for like a day, 7:30 to aggregate data for these three values. Does that sound good to you?
Yes.
Okay. And then if we can talk about how internally MapReduce work, but it's like very if I talk about it, it's very simple. We get, let's say, like the events in the map part, like the MapReduce is actually divided into 3 steps. So MapReduce is like it's a 3-step process, three-step process, where in the map step we actually uh, receive the raw event, and raw event is not transformed into something like this. I mean, we have raw event and we do one. One is like the count, and we'll have essentially many such counts. I mean, we'll have also, let me just copy it. We are now, let's say, event ID 1, event ID 2, and we'll have many such maps. And we have inside MapReduce, we have like master job, which orchestrate, I mean, which spins up multiple worker nodes, which is essentially taking the role of mapping events within that partition. I mean, it reads from the data lake. I mean, each mapper picks a partition, and for that particular partition, we run a map function, which is run on a map machine, which is nothing but a simple machine.
Okay.
And then when we do sort and shuffle and sort basically, shuffle and sort, where we basically now bring up all the events together. Let's say event ID. So now it will have a list of one. Let's say counting. I mean, how many time it was appeared. Similarly for others, and reduce it. It is exactly the reduce function that we have in our Java programming language, where we do a simple summation for all those event IDs, and we get something like this: event ID, let's say 1, it has, let's say, 10K count, right?
Yes.
Right. And now these values are stored. I mean, these values for all the event ID will have, like, let's say we have billion videos, but we really don't care about storing billion videos event IDs with some storage. And I'll come back into the storage day because I see a drawback. And now let's say we store it, and then we use a min heap to maintain a min heap to get the top K elements from it. I mean, now, so I'll propose all these event we can store in our, let's say, Cassandra DB or a Dynamo DB.
Any particular reason for using Cassandra or Dynamo and not a relational database?
Okay, so multiple reasons. One reason, which was like our structure is already flat and denormalized, and we don't have any other database where we want to do make relational joins. We don't have any ACID properties to maintain. And this, and at the point when we say MapReduce job, we want something which can easily be queried as well, and it can scale as well with the scale, because Cassandra, I mean, both are like almost does the job similarly. I mean, Cassandra is like your wide columnar DB, where we store something like this. We'll have a map of map, and we have our, let's say, event ID, let's say 1. Let's call it E1, and within that E1 we'll have different columns. The column could be count could be, let's say, 10K, and we can also store multiple things. Let's say count of this video within US. Let's say it is, let's say, 1K, and we can have multiple such data, and then also we can have,
in short, instead of diving deep into the counts.
Yep. Sure. So this is how, I mean, also Cassandra is like write heavy. It's very good for append only operations, and that's the use case for us that we have. We'll be appending. The operation is very simple. We just want to append a good number of events within our Cassandra.
Okay.
And so let's DB. So let's say we'll have our database here, where we simply populate it here, and this is how our schema would look like for it. And this database would be, now essentially this is like our slow path. I mean, this is like our slow path where we actually care about getting the accurate results. And This is our DB where we actually serve. This actually holds the source of truth uh, for each device. Also, we can discuss a bit more about it. That within Cassandra we can have a partition key, where partition key would be nothing but the event ID, and we can have a cluster key which essentially maintains within that partition how all the elements will be stored. I mean, in what fashion, like ascending or descending. So within that schema, we would say event ID would be my partition key, and count would be my cluster key, which is essentially we can store it in our descending fashion so that we can directly return. I mean, now it is very easy to query. We'll do select star from, or let's say select star from our table, which is whatever table name we have, where sorry, this will be not on event ID, it will be rather on the date, because we want to store date wise. I mean, for each date, what all values we have, right? And it will be event ID only. Sorry. Yeah. So this will be event date. So now, and within for a particular date, all those events. I mean, for a particular date, let's say this is the date. Let's say where date is, let's say whatever. Let's say is today, and we can say limit 10 to get the top 10 for last one day.
Yeah. Okay.
Or it could be like I can I think I get it right. Yeah. It's pretty straightforward. Yeah. And this is how it like overall. Okay. It would be for. I mean, also then we. And also we can talk more about that. I want to talk about more about the service layer where we are. I mean, this is our fast path where we serve data quite fast, like with some millisecond of latency, but we have an approximate result, which is fine when we want to capture viral events. Okay. But this global top K and the host machine, it is not currently storing the values of global top K and I mean heap within the memory. Okay. So rather than doing it here, I would rather suggest having a Redis in-memory cache where we just drop all our top K within our Redis, and then we can also use something called Z set, or like sorted set within the Redis, which will essentially help us to query even faster for like top K in like descending order. Does this sound good to you? Mm-hmm. Okay, so this is how overall it will look like. Do you have any question like on it, or do you want to me dive deep on any of the anything?
No, I think we have already dove deep enough into all of the components. Could you focus more on the caching part? Like, why have you decided to use a sorted set, and are you also planning to run some kind of cron job to periodically come up with the fastest?
No, not really. I mean, see, our host machine was, I mean, this is a single point of failure. I mean, let's say our host machine dies, which is a service layer, because all the data was stored internally in the RAM for a faster lookup. Because, I mean, when you want to query your data, we want the fast retrieval, because essentially the idea is to have a fast path so that we can send back the data quickly. So that makes sense to have it within a RAM. But this doesn't scale because a single point of failure is there, and let's say if the machine goes down, your data is lost. So to deal with that, this host machine again will do. I mean, this thing is doing some bunch of tasks. I mean, one is like doing like merging local top K, and then storing these. I mean, not storing. I mean, just simply sending, or I mean, storing it in Redis. Merging, and then min heap for getting global top. I didn't talk much about how min heap is being used, but I assume that it is a very classical problem of DSL. One can obviously go and check out on leaked code. But yeah, storing Redis, why? Because we want something to be retrieved fast, and we use the same idea that we want to retrieve fast. We want something in memory RAM to retrieve fast, and Z sorted said it helps us to. Similarly, the way we remember that we had our this thing, Cassandra, we decided to have a cluster key on count, so that within that partition, I mean, a single partition is nothing but a date. I mean, we can have 30 partitions. 30 partitions for each date. I mean, for last 30 days. So it is very simple. For let's say I want to query for last 7 days. I'll go in each partition for last 7 days. Like one partition is one day. I know within that partition already my events are in a sorted fashion of descending on the count. I can just simply do a get. So the similar way, we have something for Redis as well. So within that Redis, we can have a key, something like this. Like we can say top K, and then we can have like event ID, and then window, let's say window. That's it. And then we can store, for this key, we can have a value of count and the event ID if you want. Or again, just count is fine. But you can also show multiple other metadata as well. Let's say the user want to fetch the not we talked about global top K, but it could be like regional top K. Like give me like US, what was the top K for US? What was top K for India? And also it could be for category as well. I mean, we can have a category wise top K. Give me top videos, gaming videos, top vlogging videos and on whatnot.
Yes.
Right. So we'll have something like this stored here, and it will look like something like one of the event will look like, let's say, E1, 2, 3, and then windows, let's say, last 1 minute. Or just let's say last 1 minute, or it would be timestamp basically. Rather than window, it should be timestamp.
Okay.
Timestamp. And let's say I just altitude it so that. So now we'll have all those events accumulated within the set, and now we can easily query for, let's say, give me last 5 minutes of data. So the last 5 minutes, let's say from current till last 5 current to -5, we'll get that timestamp. We'll fetch from here our Redis, and we'll get back to our service layer and again do the global top K calculation and return it back to the user.
Okay, makes sense.
Yeah, so this was my idea of having a Z-sorted set Redis, which is like, and it can easily scale because in Redis we are only storing let's say thousands, max 1000 K value. So that, because K is also flexible here. Let's say the user wants like K is equal to 100, give and retrieve me 100 values, 100 top elements. So we can also do the same thing with this Redis. I mean, we have all those values in place to query, and similarly we have all those values. I mean, the limit is K, I mean here. And the max number of events that will be showing, which is like event ID, unique event ID, will be bounded by 1000, which is like the max we decided.
Yes.
So at max in any partition, there will be 1000 rows. When I say rows, I mean 1000 columns, because it is wide common data.
Are you planning to apply some sort of pagination strategies to display the results, or do you think that for K is equal to 1000, it's not really required?
I think there should be a pagination because in any typical UI, we shouldn't retrieve all 1000 values, and then we can. I mean, that's a decision, product decision, whether you want to have pagination on the client side or have a server-side pagination. If you have a server-side pagination, it's not a big deal. It comes out of box, and even in Cassandra, and we can do some tweaks in our host machine service layer, and in our, and we can decide a page size of, let's say, 100, and then we changes the page number whenever the new request comes. I mean, again, it's a product decision whether we want to have a client side where we send all 1000 events, and then there's a client side pagination happening, which is fine, and it can easily handle it. Like I can assure that 1000 is not a big number for UI to handle. We can have a client side pagination, or also if it grows, I mean, but it really matters. I don't think beyond 1000 it won't be the product fit, because no users will go till the last page to see, because we just want to see the viral events and the top trending events.
Makes sense.
Does that sounds good to you?
Yes.
And also, I want to, I mean, this whole architecture is called Lambda architecture. And if I remember it correctly, it was coined by one of the creator of Apache. I mean, Apache Hadoop, Apache Storm, I think. And where the and and the Lambda architecture is nothing but data processing design pattern, which we just did, where we, if we see the Lambda sign something like that, there's a single source of event, which is now getting split into two, which is like one is a fast path for us and the slow path. And it essentially says, the Lambda architecture for these kind of applications essentially says that we have a architecture where we can also, I mean, the question is, how do we handle high throughput and low latency? I mean, high throughput, accuracy, and low latency at the same time. Let's say user queries for, I mean, this is very much extensible. This current design is very much extensible to also answer query like, give me top K for last 25 hours. So for that, I have an accurate result. I have an accurate result for last 1 hour, which I can get it from my slow path, which is already stored in my Cassandra DB. I can get that last 1 hour. And also from my fast path, I can take last 1 hour data, append it, and send back to the user. Which is, again, it's quite accurate because last 24 hours is highly accurate and 1 hour is fine because we just risk it. And it is a classic paradigm and decision choice and trade-off that we have to make against low latency versus high accuracy.
Okay. Yeah, that sounds reasonable.
Yep.
Yeah, so you can have a quick look at anything else you're thinking of discussing. To me personally, it looks good.
I think the only thing I missed discussing is the content sketch, but it's mostly it's mathematical. But I want to just give a quick overview of what is CMS, which is content stack. It is essentially used. It's a probabilistic data structure similar to Bloom filter. Bloom filter is a very popular data structure. It has a very good traction on internet. As if we try to search Bloom filter, which will seem. I mean, the idea is to for Bloom filter is very simple. Like, two ideas to just find whether a particular element is a part of set or not.
Okay.
Right. So, but here we want to count the frequency. I mean, count the recurrence of particular in a data stream. Essentially, in a data stream, content sketch plays a very critical role. I mean, it essentially scales with the problem that we have, that the scaling events having like QPS and the unique videos as well. So CMS like a 2D array of, let's say, n cross m, and we there are only two parameters that essentially defines how CMS is used. So again, in product call, we have to come up with a number. Let's say, this is product call. Are we fine with 99% accuracy? I mean, 99% accurate results. If the product say yes, we are fine with 1% not accurate result, but 99% it's working fine, which is like only 0.01% of the time the results are not accurate. And the other thing is the probability of this going wrong. I mean, how much is like our how much we can compromise on the error probability. Error probability is like, we say, okay, 99% should be accurate. Only 1% of the time we are okay saying that this can go wrong.
Okay.
Right? And then we have two mathematical. I mean, this was again thrown by a Euler's mathematician. So Euler maths comes into the picture, where we have E, which is like our error margin, which we should just discuss error margin. And this is if I remember correctly, this is calculated by I think the Euler number divided by Euler number is nothing but 2.718 divided by the accurate result that you want to have, which is 0.01, and essentially gives you to like 20, something near around 2700, which I consider at initial phase, because it's a very common number when we design this kind of problems. And then the other is like probability number, like how much confident that we are that the results will stay 99% accurate. So that is something I don't know the mathematical representation of it, but I'll just say delta. Yeah, delta is a correct number, which is like we take log of base E Euler's of 1 by the probability distribution that we are saying here, which is like 0.01 again, which turns out to be somewhere around 7 or 6. That's how we decide what will be the width and the size of the basically width and the depth of the CMS, where the width controls the error margin, because it's very obvious. The more the width has, there will be less collision. And how it works internally is very simple. When let's say we receive an event ID, we now, since we say the height, basically the height is 7, so we have 7 hash functions, 7 hash functions, and 2700 columns, which is like cells essentially. Whenever an event came in, we hash this with all 7 functions, and we actually go and increment within that cell. So let's say if this is your count sketch, and an event comes, so let's say we'll go and basically maintain basically increment the value there within that content sketch. And when we want to retrieve, and also whenever there's a collision, I mean, obviously because there's a limited number of columns, but an unlimited number of events happening, or unique events, there will be collision. We simply increment the same. I mean, let's say there's a collision on cell 1, if there's already number present, we'll just do +1 on it on collisions. And then on retrieval, or when we query, we take the minimum of all this. I mean, again, let's say the query came for give me the count of this particular event ID. Event ID, let's say 1, 2, 3. We take a minimum of all, minimum of all cells after the hashing. I mean, hashing gives you the cells. All 7 give you some cells. So let's say there are 2,700 cells. So from all 2,700 cells, basically all 5, basically hash function will give you 1 cell. So out of all 5 values or 7 values, you'll take minimum. Let's say 2, 12, 13 or something, or 100, or you'll take the minimum.
Okay.
Minimum of all cells. This is how confidence can, and it hardly takes any values. I mean, hardly takes any space. So it's no hit on your consumer nodes, and it can essentially scale up to. I mean, it can easily. It's like shock absorber. It doesn't grow. So you can completely replace the hash map, and the idea is simple to implement as well. Then everyone has a local CMS, and at the end we just do a matrix addition of all the CMS to get the global top K for the CMS.
Yeah. Okay. I think that sounds good.
Okay. And I think even I don't have anything else to make much improvement. I think this is all it.
Yeah. I think we are also at time, and this looks good to me. Will you just briefly discuss one you mentioned that you want the system to be highly available, the 4 nines principle. So just orally tell me some other strategies that you can think of, or is the current design catering to everything in terms of availability?
I think having multiple see, availability is mostly taken care here, because so let's say if any of the partition goes off, partition essentially is a machine internally Kafka, which maintains the Kafka broker, maintains what all partitions we have and how to store the raw data into the partitions. And the partition is now actually the hash function. We do hashing on event ID and then decide which hash or which partition this event belongs, and all the events similar events belongs to a single partition. Let's say that partition goes off, well, like it's dead. So Kafka is very much I mean, it come out of the box, it identifies, it triggers a rebalance, and another consumer node, basically if the partition goes up, it spins up the new partition and provides, I mean, transfers the data. I mean, for every partition there is a duplication as well. So let's say master slave. So if one goes down, there's another one sitting to take over it, because it has essentially the copy of it, and which takes over it, and then we have other consumer rebalances and start consuming again. And even let's say consumer goes down, one of the consumer goes down, Kafka is able to identify whether like one of my consumers died. So it will pick, or my system should be like auto scaling should be enabled. Let's say one of my consumer died, it should either retry or restart or add another consumer node. And I think availability of only this service looks a little bad to me, because we don't have. I mean, initially the problem was I was storing the global token within the memory, but we decoupled it, storing in a distributed Redis in memory. But if this service layer goes down, so we won't be able to serve the fast path. So again, this is, I mean, having a single host machine it's problematic. Maybe we can add more machines here rather than having a single machine catering all the. And we can have more like parallelism there.
Okay.
As well.
Yeah. Okay then. Yeah. This sounds good to me. If you have any other follow-up questions for me, let me know.
No, nothing from my side. I think that's it.
Okay. So thank you, Anubhav, for taking the time for explaining this question.
Thank you so much. Thank you so much, Sanjay. If you have watched the complete video, that's great. Now you know how would you approach this kind of problem in an actual system design interview. Now it's quiz time. There were some follow-ups that was not covered in the mock interview, but could be potentially asked to you in your system design round. I would really appreciate someone answering these follow-ups that I'm gonna tell you in the comments. So the very first and obvious follow-up could be, why do we even need two different data sets for storing our results? In this system design, we discussed that we have one database, Redis, where we'll be storing a prox result, and we have Cassandra, where we are storing accurate result. Why can't we have just a single database to store both of the results? The second potential follow-up could be, how would you be calculating the data, basically top K, for last 7 days, last 30 days? This was not discussed in this mock interview. Here, you would need to talk about how one day, like you have 1 day data for last, let's say 30 days, you can't aggregate them and result and return for 7 days and 30 days because there will be a data loss. You can't simply aggregate last 7 days top K results, sum them and return for 7 days. Classical problem that we discussed, lost on the tail problem. Then how would you be doing for 7 days and 30 days? Basically weekly and monthly top K. Another potential follow-up could be related to the client side. Imagine your interviewer can ask you this question that we have to imagine that a user clicked or watched a video at, let's say, time 6 p.m. And however, he was under a subway or was in no internet or low internet area, and the phone finally reconnects, let's say, after 5 minutes. This 5 minute delay can cause us, it can lead to data loss because we might not be aggregating it in the 5 to 6 p.m. of the data, right? Because the event happened at 6, but it didn't reach to us. We might need to consider it as how would you deal such kind of late arriving events that we are receiving. Another third follow up could be from the slow path, where we are actually dumping raw events. Basically, these are the raw events that we are sending to our Kafka topic, and our consumer groups are dumping it in a data lake or let's say S3 or a GCS bucket. So here, let's say if we are dumping 100k events per second, 100k QPS, so serving them as a JSON file will cost us like a lot in our storage fees, right? So how would you optimize the MapReduce because it will run very slowly if we try to just simply pull off 100k events per second from your data lake to process. That too is a JSON. How would you optimize this? So these were some of the follow-ups that I had in my mind, which could have been asked in your interview. I would really appreciate someone of you answering those in the comments. Also share feedback, what you liked and what you didn't like, and what if was added would improve your experience. Thank you so much for watching. Do subscribe to Unpuffin Tech and comment what next system design problem you want me to cover. Thank you. Bye.